Okay, so remember what we're doing, right? We're in the middle of this gigantic proof of Dirichlets theorem. We've reduced the problem down to showing that the sum of these Dirichlet characters over P, right? We've reduced the problem to showing that this sort of thing, the P ranges of the primes, is finite as for non-trivial characters. Right? That's the game. We want to show. This was the first reduction. We want to show that this thing is finite. Right? If you can show that the thing is finite, then we're done. So, okay. And we are trying to show, we're just about to get the product formula. Right? So, right, we want a product formula for L-functions. We want the product formula for L-functions, and it's analogous to the product formula for the zeta function. Right? Here it is. Right? For s greater than 1, we want to show that the L-function, and here's our current goal, to show that if we look at this thing, which you remember is the L-function as L as chi, we want to show that this thing is expressible as 1 over 1 minus chi p, chi p to the s, as p ranges of the primes. This is the analog of the product formula. So the first thing to notice is that both sides converge. Okay. This side converges. Why? Well, the chi's are these chi's are the Dirichlet characters. So what kind of values do they take? 0 and 1, right? So this is basically controlled by sum of 1 over n to the s. N is bigger than 1, and so this thing converges, right? Same sort of argument for the right side, right? We just proved in the last class that if you have an infinite product, we prove the infinite product for complex numbers, right? And so this sort of thing is going to converge as long as the sum of this thing converges absolutely. As we just noted, that thing, well, not exactly, but this thing is controlled by this thing, which converges absolutely, right? And so that both sides converge. Is that all right to everybody? Do I need to write it out, or is that okay? So so this converges since I is smaller than 1, right? And this thing converges by the previous lemma. Right? The product, the infinite product. Infinite product. So it's not okay. So these two things make sense, and so we're going to look at the difference of them, right? Right. We're going to look at the difference of these two guys. And we're going to control it by, as usual, breaking it into pieces that we understand and pieces that we understand and are easy, right? That's analysis, as I said last time, right? You break the thing into pieces and you throw away the easy ones and then you think about the hard one, right? So here's what we do. We say, well, I'm going to break this into this sort of thing. I'm going to take the infinite sum and subtract off, right? So we've got this infinite sum guy and subtract off finite sum guy. Right? So and that's what I'm doing now. Right? Of course I need to add on that finite sum guy. Right? And then I'm going to subtract off the sort of a finite product guy, but it's going to be a little bit. Let me write it up here. So I'm going to excuse, I'll say that my advisor was extremely bad at board work. He would just like have to these things, he would lay on top of things, and just hope that you actually concentrated enough that you'd actually see something like that. Anyway. Okay, so yeah, I actually say that a lot of my teaching style is derived from this imitation of my advisor. Of course, cannot compare it. It's the way that you explain things. Okay, so we take, when we have these infinite guys, right? We have these infinite guys, and we subtract off finite parts, right? So n equal 1 infinity, and less than equal to n. Right? Add on the n is equal to n. We subtract off this sort of term. We take the primes of size less than n, and further we take the partial geometric series. Okay, so Ts. Okay, which we can do. This is a geometric series because the Dirichlet characters are multiplicative, right? This xpm is the same thing as xp quantity to the n, right? So this actually is the partial geometric series for this thing. Okay, and then we add on that same thing, I, and then there's m, right? And we subtract off this thing, p prime less than n, 1 over 1 minus 5p d to the x. Right? And of course we have to add that thing on. And then we subtract off the infinite product. Okay, so this one's the finite okay. So right, so some of these moves are pretty obvious, right? Right. This move is obvious, right? You've got this infinite series. Well, you're going to approximate it by the finite. That thing converges to this, right? So we can throw that out, right? Similarly, for this last term, we've got the infinite product. Well, this thing converges to that, right? So we can chop off this bit, right? So immediately we see that these guys we can make smaller than whatever, right? Because we just said that that the sum of this product converge, right? So we can make those things converge to the infinite things. So we can make this smaller than epsilon. Okay. 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 So next, what is easy? What else is easy? This is easy, right? If we look at this thing, 1 over pi p dds plus dm over p at kms, right? We use the fact that this is that the function is multiplicative. That pi is multiplicative, and we say, oh look, this is a geometric series. This is the partial sum of the geometric series. As m goes to infinity, this thing converges to this. Right? There are only n. This is a finite product, right? A finite product of a bunch of partial sums that converge to these infinite series, right? So we can make this smaller than whatever epsilon. Okay, do you guys see that? So this piece is also easy. Should I say it again? right? Right here, if you look at each of these things, this is the partial sum of the geometric series whose limit is this, right? So if we take m large enough, right? If we take m large enough, then we can make this difference smaller than epsilon, right? Because each of these guys converges to this thing, and it's a finite product. It's a finite product. That's the deal. It's finite. So this can be made small as well. It's almost as trivial as the first two. Okay. So then the only one that is a little bit complicated is this one, right? This is the tricky one. Tricky? I don't know. Right? So we're looking at this thing, I and s, and we subtract off this sort of thing, right? And we're allowed control over m and n. Okay. Although actually we've already sort of set our we've said that our n is we've taken our n to be we've already set our n in some sense. Okay. So we set our n so that this thing and that thing are small.
I can also already set our n by saying the upper range will look like each other's n.
That's true, but we can still make it bigger. We can still make it bigger, right? So and in that sense, we could make our n bigger as well, but it's the n that's the important one. Okay, so we're looking at this thing, right? We're looking at this thing. We want to make this thing small, right? What do you think? Okay, well, the n is fixed. Okay, the n is fixed, and so we're only dealing with integers, less than or equal to n, right? And so each of those guys has a prime factorization. We play the same game as before. We take our m big enough. We take our m bigger than n and big enough so that all of the factors of these guys show up over here, right? So that gives us basically says that that these guys that all the terms that show up here are encompassed over here. All the terms that show up here are encompassed over here. Okay. The only thing is that you also have some extra terms, right? So there will be some other terms, right, for n bigger than n, right? Not all of them, right? This thing here will, if you look at the difference of this thing, well, this thing will cancel off with some equal terms over here. But this thing will also generate some other terms. Okay, it also generates some other terms. But we know that this tail is small because we just required, right? We just required that the difference between these guys is smaller than epsilon. Okay, so this thing also can be made smaller than epsilon. Okay. And that's the end. So that's how you. This is the only piece that's a little bit tricky and requires understanding, requires using the fundamental theorem of arithmetic, and also understanding that when you take the products here, you get terms in the sum here. So that is the proof. That's basically the proof of the product formula for the L-functions. Any questions on that? So again, let's say the first term and the last term are trivial, simply because those finite guys converge to these limits, right? The third term is also trivial, right? Because this is a partial sum of the geometric series, which converges to this value. And so this can be made small. And then the last thing, the only thing that's a little bit tricky is just to understand that the difference between the sum, the finite sum, and the finite product. Right? And that you see that the difference is actually some terms like this, and it's not all of the terms. It's not all of the terms, but it's just some terms. But they can be controlled in size less than epsilon. Okay, that's all I'm going to say about that. Okay, so the cool corollary of this is the fact that the L function that corresponds to the trivial character is actually the zeta function up to a constant. I hope that once I stop teaching you guys, that I'll stop being sick. No, I'm joking. Your sickness, your teaching this class does not contribute to my sickness. Okay, so here's a corollary, which is kind of nice. Right? If you look at the trivial Dirichlet character, remember what this thing is? It is 1 if n and q are relatively prime, and 0 otherwise, right? So if q, right? So this is the trivial Dirichlet character on C star q, remember? So if this, if q has a prime factorization, is the prime factorization of q, then L s phi naught is actually the zeta function times some constants. So these L functions really are in a very precise sense, generalizations of the Riemann zeta function. So this actually equals 1 minus p1 to minus s, 1 minus p2 to minus s, 1 minus pn to minus s, times the zeta function. And this is actually just a trivial corollary of what we just proved. Right? We just showed that that summation chi naught n ps n from 1 to infinity as this product form. We just showed this. Previously, we showed that 1 minus 1 would give me s is zeta s. Right? That was Euler's product formula. Right? Euler's product formula and Dirichlet's product formula. Right? And so you say, well, what's the difference? Right? This thing is going to be 1, right? Except when p and q are not relatively prime, right? So this thing is equal to 1, except when p and q are relatively prime. That is to say, when p doesn't divide q, right? Because p is prime, right? So what terms are missing are the terms where p divides q, right? The terms that are missing are P equals P1, P equals P2, blah, 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 right? And so you see that the difference is calculus. Right? If we multiply, this on the bottom, right? If we multiply this by 1 over 1 minus 1 over P1s, 1 over 1 minus P2s, oops, P2s, 1 over 1 minus Pns, then we get the zeta function. Right? In other words, the zeta function divided by that is the L function. Okay. It's extremely bad. Not I really crossed the line in terms of bad notation, but you see what I mean. Right? I'm going to call this thing Z. So notice Z times this is this times Z, which is the zeta function. Yes, thank you. Right? Z times this times Z, right? These are the primes that are missing, right? The primes that are missing are the guys that divide Q, whether that's P1 through Pn. Right? So we throw in those guys, we get all the primes, but we remember that the product over all primes is the zeta function. Okay. So this is a pretty cute consequence of the Dirichlet L-functions. Okay. Any questions? Jennifer, no, it's good? Okay, good. And the only thing that you have to think about a little bit is this, right? What's chi, right? Chi naught is the guy that tells you if these things are relatively prime. Okay. So it's going to be, and for most p's, if we feed in p here, right? If we feed in p here, we're asking, are p and q relatively prime? Well, p is a prime number, right? P is a prime number, so the only way they're not going to be relatively prime is if p divides q. Right? The only way they're not relatively prime, right? Because q is not going to divide p. I mean, they're not going to have any common factors because p doesn't have common factors, right? P is prime, so the only factors it has are 1 and p. Right? So when can you have common factors? When p is one of these primes. Right? The only time you have common factors is when p is one of these primes. It's not hard. You just have to maintain your sanity. Okay, so now comes the crazy stuff. Okay, here we go. So this is the easy stuff. And at the end of this lecture, I'm going to say, now actually comes the crazy stuff. Because it's actually after this lecture that things get deep. So, like, the author is saying, now we come to the deep part. Now we come to the deep result. And that happens after this stuff. Okay, so things get a little crazy here. Actually, it's really hard. Okay, so so I'm not going to say why we want to do this yet, but basically we're going to go for a second reduction of the problem, and that second reduction will involve basically involve taking. So here's basically what we want to do. And we just showed this product formula. Infinity, like, equals the product. Okay. What we would like to do, so I guess I will talk about it. So what we would, here's what we would like to do. We would like to do this. Okay. We'd like to take this thing, and then we'd like to hit it with the log, just like we did, in the case of the zeta function, right, to show that that thing was infinite. So we'd like to hit this thing with the log and turn this thing into the sum of logs. Right. And then use the property that we already proved, that this is going to be some sum, plus some constant, basically. Okay. Because remember, our goal is to control this thing, right? Our goal is to show that this thing is finite, right? And so what we'd like to do is to, here we've got log of the L function. Okay. So what we'd like to do is say controlling this thing is equivalent to controlling this thing, and we can do it. Okay. But the trouble is that is defining the log. So we've already done the log for this guy. This guy was log 1. Okay, and log 1 had the properties that we wanted. So this part actually we've gotten already. But we don't have a good way of defining the log of an L function. Okay, and so that's the difficulty. We need to define the log of the L function. Okay, and that's actually going to take the next hour or so to define the log of the L function. Or maybe not too long. Maybe only 20 minutes, depending on how fast we go. Okay, so the trouble is to create the appropriate definition of the log so that, and it's going to be called log 2, so that log 2 of this side equals log 1 of that side. Okay, so what definition of the log will we use, and how do we know it makes sense? Okay, this is the difficulty. So you should ask, and I'm asking, I'm not sure of the answer. Why can't we just use log 1 again or something like that? Evidently not, but let me think of, I don't know myself why, I haven't thought of myself. There's probably some obvious reason why not. Anyway, think about it. Okay, so here's the trouble, right? Here's our goal, to define logarithms of L functions. Right. Okay, so here is what I'm going to call the technical proposition. So here it is. Let pi be a non-trivial Dirichlet character. Then one, actually, the definition actually makes sense for s bigger than 0. So the definition of the L function actually, the series actually converges for s bigger than 0, not just s bigger than 1. So we can actually extend that. 2, this thing is actually continuously differentiable. 3, there exist constants c and c prime such that L s chi is 1 plus big O of e to the minus cs as s goes to infinity. And 2, the derivative is of the order of e to the negative c prime s, again as s goes to infinity. And we need these things to create the logarithm for the create the definition of the logarithm. Okay. So here is a what they call the key lemma. Okay. Phi is a non-trivial Dirichlet character. Then the absolute value of the sum of chi n from n equals 1k is smaller than q for n k. So no matter how you sum it, it doesn't leave the q ball. Okay, so this is actually pretty straightforward. So recall that summation chi n from 1 to q is 0. We did this earlier. Right? If you take a character and you sum it over the whole group, if it's a non-trivial character, then the sum is 0. Right? So this follows since pi is non-trivial. Right? And then, right, we're interested in this thing. So, well, you just break it up into, the proof is sort of obvious at this point, right? Right, every time we sum the q, then we get 0, right? So we can basically throw out all but less than q terms. Right? So here's what we do, right? We write k as aq plus b, where b is between 0, and q by the Euclidean algorithm, right? So then this sum chi n from 1 to k, well, that's the sum over these first guys, right? N from 1 to aq plus the sum of n from aq to aq plus 1 to aq plus b. Right? And the sum over these guys is 0, right? Because it's just, this thing is periodic, right? And we're going from 1 to q 8 times. Right? So this is 0. Right? Okay, so in absolute value, then, right, we say that we're taking a sum of fewer than q terms, each of which is smaller than 1, less than or equal to 1, right? Because the Dirichlet characters take on values 1 or 0, right? So this is smaller than q. It's taking a sum of fewer than q terms, each of which is in magnitude smaller than or equal to 1. Okay, it gets worse, much worse. Okay, now it'll get worse. Okay, prove. So let's prove the proposition. So I'm just going to say easy to see. So just easy to see that that the series for L and the series for L prime, they both converge uniformly and absolutely for S bigger than 1. I'm going to say that because it's true, and that's not the interesting part. The interesting part is maybe showing that that this thing converges for S bigger than 0. Okay, and this is where the key lemma will come into play. So okay, so let's show convergence for S bigger than 0. Right? I want to show that this thing converges for S bigger than 0. So just for notation, let's let S of k be the partial sum of these terms. No, partial sum of A of j on 1 k. Okay, and let S0 be 0 for convenience. Okay. Then we do something pretty straightforward. We're going to rewrite this thing as as another series that converges absolutely and uniformly. Okay, so we're going to rearrange this thing, and we're going to see that the rearrangement converges uniformly and absolutely. Since that rearrangement converges uniformly and absolutely, then so does this thing, because we have the absolute convergence, which means that we can rearrange. Right? That rearrangement doesn't change the convergence. Okay, so that's the idea. We're going to take this thing, rearrange it, and turn it into something that converges absolutely uniformly. Okay, so here's what we do. We do something very simple. Yeah. So we rewrite this as sk minus sk minus 1 over k minus. Nothing is happening. Right? This is the sum from 1 to k. We subtract the sum from 1 to k minus 1. That gives us the top term. We express the top term as the difference of this sum minus the sum right before. That ends right before the top term. Okay. And then we do something even less interesting. We break that. Into these parts. We break it into two parts. We don't need the k equals 1 term here because S0 is 0. Okay. And then we shift the index. So that we go from k equals 1 to n minus 1. Right? Well, if we were shifting the index down, then we have to shift these guys up. Right? So we get k plus 1. Yes. Right? And we're going to take this one from k equals 1 to n minus 1, sk to k to s, and let's put the last term over here. Then you can guess what's going to happen. We can combine these terms, right? Summation sk 1 over k to the s minus 1 over k plus 1 ds equals 1 to n minus 1 plus this Sn, excuse me, and this. Okay. And this is the this is the term that we're going to, this is the thing that we're going to show converges absolutely and uniformly. So, right, if we consider, let's consider this thing. So consider sk 1 over ks minus 1 over k plus 1 ds. Okay. Well, this thing is the sum from 1 to k of the Dirichlet character, right? So we have control by the key number. This thing is smaller than q. In modulus, this thing is smaller than q. Okay. So the only thing we need is to think about this thing, right? But this thing, right, is when we think about it, right? This is controlled by the mean value theorem, right? We can think of this as this is controlled by the derivative of x to the minus s, right? As x ranges over k equals 1. By the mean value, this is following that by mean value theorem. So this is by the key lemma. Right? And this is by the mean value theorem. Right? And so you get qs over k to the s plus 1. Okay. So so if we're looking at this series, right? If we look at that series, we see that the terms are controlled by these guys, right? And if we look at from k goes from 1 to infinity, right? This is and s is bigger than 0. You see why we only need s to be bigger than 0. As long as s is bigger than 0, then this is 1 over 1 over k to the 1 plus epsilon, right? Summation 1 over k to the 1 plus epsilon converges. Right? Converges, and so this guy converges absolutely and uniformly. Okay. And thus, the original guy also converges absolutely and uniformly for s bigger than 0. So pretty cool, right? It looked like we needed s to be bigger than 1, but in fact, because of the cancellation that occurs in the character, we actually only need s to be bigger than 0. So you do the same sort of thing when you consider the if you take the series for L prime, you basically run through a similar argument, and that will show that the derivative is continuous. Okay. So I'm not going to do that because that part is basically the same. Are people okay with what we're doing? Okay. So we wanted to show that this thing actually converges for s bigger than 0. We play this game and use the fact we rearrange the thing and then realize and use the fact that the s of k's are bounded. Okay. We use the fact that the s of k's are bounded by q, right? And then we've got this thing, which is when we sum that thing, that is, that thing converges uniformly. The book says that they use the summation by parts formula. Actually, they don't. That's all they do. The only thing that's done is this trick, which does not deserve the name of summation by parts. so in the last 4 minutes, let me see if I can definitely do we want, so here's the point that we're still in the middle of the technical proposition. Okay, this is the third part of it. Okay. That L S chi is basically like 1 plus something where e to maybe see s as system. Okay. But actually, this is trivial. So why am I doing there's only 2 minutes left. So let's look at this. This is summation of n over ns and equals 2 to infinity. Because we just subtract off the first term. We control this guy with an integral, right? The integral from 2 to infinity of x to minus s dx. Right? You get, when you integrate this thing, you get 2 to the minus s, 2 over s to the minus 1, and that's the end. Right? You take let c belong to. Right? And then this thing, right? So for s bigger than some number bigger than 1, then this thing is smaller than some constant. Okay, so you do have to ensure that your s is sufficiently big. It has to be bigger than 1. Okay, which is okay because s is going to infinity. Right, so then this thing is bounded by some constant. Right, so this is your order 1 term, and then this is of course your e to the minus cs. Okay, and so let me finish up by saying, and you can prove the other bound for the derivative in basically the same way. So what's the point of all this? The point of all this is to what is the point? The point of the technical proposition. What was the point of that? It's so that we can actually define the log of the Dirichlet function, of the L function. Okay. It's so painful, right? All we want to do is just write log here. You think, is it so hard to write that down? It actually is not so simple to get the log that gives us the rate, that gives us that quality that we desire. Right? Here it is. We define log 2 of the L function as the integral from minus the integral from s to infinity of L prime over L. Okay. And it turns out that this is the function, this is defining the log in this way. This will give us the necessary formula. This thing that this will give us that first step in the reduction that we so desire. And we'll reduce the problem to understanding the log of LSX, or understanding actually LSX, which will be the difficult part. The